thought I had looked into it, and I thought that you can get the whole thing done. Like you just had to like do some online chat with.
I met with Mary Louisa.
Oh, so
Yeah, but since I'm moving off
oh,
campus anyway in May, like I'm just gonna wait to get my
I gotcha. Is this cooking now? Yeah, there we go. Okay, so make sure you sign up for the hackathon. Let's. All right, so we have this thing pretty much designed, right? We're going to create some shared memory at the server side. The server is the only one who's allowed to modify that shared memory. We've already kind of introduced a possible issue we might bump into that we're probably going to need the semaphores for. We're not writing this part yet, but when clients disconnect, like right now, we basically decided when you connect, that's your new life. your new life. You are in this epic chat room forever. Um, which is kind of. How many of you watch anime? See, I've always tried to get into anime, never been able to. And your friend Taji turned me on. You're friends with Taji, right? Yeah. So I met with her the other day and was chatting with her about bariatric surgery stuff. And she turned me on to this um, thing on Netflix called. Am I going to mess up the name of it now? Sword something. Sword who? Yeah, yeah, yeah. And yeah, so that's like these people who are like in this VR game, and some people are there during the beta. And now the game's released, so they're in this game, but there's no log out button, and it's like a full immersion thing. So I guess they're in a coma or something. And if you die in the game, you die. So that's how this is going to work. Okay, once you're in our chat room, you're in it. You're stuck. Okay, because we decided if one of these child processes needed to go and remove somebody from the shared memory, that would become a problem because now we have this resource potentially being modified by multiple sources. So we're not going to worry about that right now. Once they join, they're joined. Okay. So we're going to have our server created. We're going to go ahead and generate some shared memory. What kind of values are these guys holding? They're going to hold the integers, which are the socket IDs for these guys to talk to. So let's start that piece. Let's just start writing the server piece of it. I have Atom open here. I'm going to create a new file. Where have I even been storing these things? Seems like I should put these on like a more like permanent type of destination, really, right? So let's go into, because I like this better. You feel like you're, yeah, right? All right, we're gonna put it on the desktop. All right, I'm gonna create a folder though. CSC450 chat server. All right, and then we'll go ahead and we're going to create a new file in there, and we'll call this guy server.c. All right, so here's server.c, and we're going to go ahead and pre-populate it with some of our shared memory stuff, and we're going to use the version of this that uses our shared memory stuff from up here. So I'll grab most of this stuff. Actually, why don't I just grab all this, and then we'll just gut what we don't need as our starting point. Okay, so we have our interprocess communication stuff, which gives us our access to shared memory, and then we also have the shared memory specific functions that are in shared memory. Standard def, this gives us things like null, and I think that also gave us like IPC create. This gives us socket stuff. That gives us string stuff, which we'll need, so let's just say that's good. All right, so we have our shared memory ID. We'll have our key. These were just some of those messages that we were sending back and forth. So for right now, let's just go ahead and we'll create like a welcome message. And maybe this is just connected. Something like that. Letting the clients know that they've attached to the server. And we won't have a child message for right now. Okay. And the first thing that we do is we go ahead and we generate we fill in our shared memory ID. So this is similar to how our sockets are working with our, these guys are just integers, which are unique identifiers. So we generate our shared memory ID by using shared memory get, passing in our key, and we get to decide on this guy. So we just randomly picked this. Passing the size of this guy. Now we're going to hold a collection of integers. So the guy we're creating here is this dude right here, right? That we decided is going to hold a collection of integers. And so we're asking it for some memory. How much memory? I believe SCH or shared mem get gives you, let me just believe that gives you bytes. SHM get. Okay. Takes a size. You're not going to tell me what that associated with the key. Shared memory segment was created. Blah, blah, blah. All right. I believe it's bytes is what it gives you. I'm pretty certain. All right. So we don't just want bytes. We want 1,000. We're going to decide how many simultaneous users we're going to have, so we could just pick our poison. But let's say we want to have 100 simultaneous users. In fact, what we could do is we can do a, here we'll just say int max users. Let's say 100, and then we're going to request max users times size of an int. Okay, because that's the types of things we're going to be working with here. So this will give us that chunk of memory big enough to hold, in our case here, 100 socket addresses, socket IDs. All right, and we're going to create. This is inter-process communication, create. So we'll create this new shared memory dealy flippy. All right, then we're going to go ahead and give ourselves a local pointer, and I actually like having the star with the variable type. So we're going to create a char pointer, and this guy's going to point to the beginning of that guy. Now, in actuality, this isn't going to be a char pointer anymore, right? We're treating this guy as an array of integers. Okay, so this is actually going to be an int pointer, and we'll call this shared memory pointer, and we'll go ahead and attach to our shared memory ID. I don't remember what null was, what these two parameters were. We can look it up here real quick. I'm not going to spend a lot of time looking at it. Shared memory address, it's a local shared memory thing, so we just put null there. And then our flag, does it tell us what the possible... How did I trigger Bixby with that? I'll tell you what, that Samsung Assistant will basically answer to anything. Just randomly starts with that. Never happened with Siri. Shared, we give a... Does it tell us what flag options we can have? Shared memory segment can be mapped read-only by specifying the read-only flag. Okay, so we're not doing that. We want this to be writable, so we can throw in a flag for this if we want it to be something more than read-write. So it looks like read-write is either the default or that's what 0 represents. Okay, then we went ahead and we copied some stuff into this, but that's not something we're going to necessarily do for ours, right? Because we're going to be adding things to this guy as we go. So the previous example that we had, we were having a parent and child proving that they were sharing that memory by copying stuff to that place in memory, and proving that things were being changed. So we're not going to mem copy that message anymore. Okay. So now we want to go back and look at our socket examples where we had our incoming connection for our HTTP server. Do I have that open somewhere? That is, what was that dude called? No, that's what this guy's called. What was our, when we did our HTTP, did we call that server? Oh, that's unfortunate. So it's not in this same, was it in downloads? I really should teach a class on file organization. Because this is how it's done, people. Apparently I do. Really depends. I have a script that runs the download to delete everything. Well, yeah, I got that too. You just go and you click on this thing, you say empty. But then I might be emptying of really important. Here, let's see. Did we put this guy in Slack? Otherwise, we'll just rewrite it. What class is this? 450. And when we were talking about the hackathon this morning, we brought up this picture. Seen this picture before? This is from, were you at that hackathon in Raleigh? It probably was when you were a freshman. Maybe it was the year before you came here. Yeah, so this is when we, when PayPal paid our way to go to Raleigh, North Carolina. We did this cross-country caravan. This was us with the trophies. It was good. Let's see. They're battle axes. This was at Battle Hack, brought to you by PayPal. 450. Do I have code? I don't want this.
You think they'll ever do that again?
I don't know if they will, but there's lots and lots of hackathons. We just need to do a better job of identifying them. There we go. That's a Josh Appel thing. Talk to the boss. I'd like to do it and really go to a bunch of hackathons, but so far it doesn't. Him and Schrammel seemed interested. So, and then I think
I just remember I told him, like, apparently your president what? Okay.
All right, so we need our socket, we need our lib, we need our inet. I think we already have the other guys, right? So copy those. Okay. These guys look so sad not without the space there. All right, so we have our libraries that we need there. Then we were doing some file stuff, but let's oh yeah, here's our main down here. All right, so we're gonna have to have our socket stuff. Let me just, I'm gonna grab all this. You guys aren't going to be in here hardly ever. In their defense, they usually ask them, what majors are you trying to plan on when you're down the hall? So if nobody said anything in technology, then it might have made some sense. Okay, so I'm going to just paste it in here and then we'll take stuff out or whatever. All right, so we have our shared memory. Then we're going to go ahead and create our stuff for our socket. This was our buffer for reading stuff in from the user at the socket. So this would be like their chat messages that they're typing. We could make the argument that we want to create this on a per child basis, but the children are going to get copies of this anyways. So it doesn't matter. This isn't a shared memory thing. This is just a, hey, you have a carry, you have a string. You have a string you can work with. We don't need that guy. All right, so here is us. Do we have a, is it like a, oh, look at that. Oh, let's just do it as I'm going through here. All right, so this is us attempting to create a socket. We're not generating, we're not connecting to the socket or anything. We just have a socket, an instance of a socket. So that's this first part with the error message that might go with it. All right. We don't have to do error checking, but if we want to, we will. We can just assume everything's always perfect and computers never mess up. So then this next section. This is where we actually attach the socket on, we're saying port 8080, so that's where our server is going to run locally here. And if we have a problem attaching to it, then we spit out an error. Okay. Then we're filling in some stuff with this struct about the type of socket we're creating. We've dealt with that stuff before. All right, then we actually bind to the socket here. Okay, so this is, we're kind of almost like connecting the socket to that port. We're binding it there. Now it's like ready to listen. Finally, we're going to actually start listening on this socket. All right, so that kind of, I guess, wires the phone up so we're capable of listening at that point. All right, so now this is what our server is going to be doing. So we'll just, we can actually probably get rid of a lot of that stuff or just reuse a lot of it. Let's, I want to keep our shared memory stuff down there for right now. So let's just do this. All right, so this says forever, while true, let's do something. What are we going to do? We spelled listening in the old Klingon. So we're going to print out listening there. And the server is going to try to accept a connection. Now this line blocks. What does it mean for a line to block? Until what? This blocks until what has happened? Yeah, somebody's actually telnetted to port 8080 on that machine. Make sense? Right, up to that point, it's the server's just sitting there waiting by the phone, waiting for it to ring. Nothing else happens after that. So this is a blocking line. Okay, so after a new connection's come in, presuming nothing bad has happened, we grab this sample code from someplace that's doing error checking for everything, so we just left it in there. So assuming everything was everything was fine, the very first thing we do is we create a child process. So if we go back to our section here, okay, the server's generated the shared memory, and now it's waiting for a user to connect. When that user connects, the server is going to spawn off that child, and then the server is going to add that socket to their list of users. That make sense? Okay, so let's do those two pieces. So connection has happened. So new chat client has connected. Create child. And maybe even before we create the child, let's go ahead and let's add them to our list. Add socket to shared mem. All right, so the socket we have is this guy called new socket. I scroll up here. Here's our new socket. New socket is of type int. Okay, so this is a file descriptor for sockets like we talked about last time. So the way we uniquely identify a socket is through its file descriptor, which is an int. So from our perspective, we're tossing an integer onto our shared memory list that we have access to through our shared memory pointer. Now we do need to keep track of how many connected clients we have, because we need to know at what bucket do we put this guy, right? So we're going to also keep track of int connected clients. When we first start up, we have 0 connected clients. So the very first client that connects, we will put it bucket 0 of our shared memory. Next one, we'll put it bucket 1, bucket 2, blah, 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 blah. Okay? Now, something I'm going to do here, just for the sake of, I'm not going to do it. I'm too lazy to do it. Okay, so we're going to go ahead and add our new client to our shared memory. So we have, what was it called? Shared pointer. There we go. Shared memory pointer. And we want to set the value at shared memory pointer plus connected clients. We want to set that guy equal to new socket. So we'll go ahead and set bucket connected clients equal to new socket in our shared memory. Make sense? Huh? Well, no. I mean, it doesn't really matter which of these two because you were kind of doing the parent is doing both of these things, right? The parent is saying, look, I'm going to add you to the list, and then I'm also spawning off a child process to deal with you. We could do those in either order. Oh, okay. But adding this thing to the array is a kind of a quick thing, so why not do that rather than dealing with the process stuff? I mean, you might be able to make an argument either way. But let's get them added to the list of connected clients as soon as possible. That way we're going to minimize maybe the missed broadcast messages we discussed last time, because technically it will take time to generate a new child process and things like that. Doesn't feel like a lot of time to us, but that might be the difference between the new client receiving a message and not receiving a message. It also could introduce a new bug. That is, he's already on the list, but we don't have anybody to send him a message. But actually, that won't be a problem, because we're not going to, if you remember this from last time, the child is not going to let the other child know to send this guy as a message. Instead, the child is just going to hit the list of shared memory things and broadcast to all of the sockets on there. So the sooner that a new connected client is in, the better for us. But certainly does not guarantee a missed message. Just reduces the chance. All right, so we'll go ahead and add into our shared memory, and this should work. I don't think we need to do a mem copy here with shared memory, but we'll double check that. So we will put it bucket connected clients, our new socket. We need to then make sure we increment connected clients. Okay, you'll find some jerk programmers that might do something like that, which is technically legal, but that's difficult code to read, right? Where you're technically taking advantage of the fact that you know how plus plus works, and you're incrementing this guy after you use his current value here. Make sense? You will see code written like that when you have older C programmers. So just be prepared. That's a thing. All right, but a good programmer will well, maybe a conscientious programmer will write it this way to make it easier, more understandable by the, by everybody. Okay, so we've added the socket to shared memory. Then we're going to go ahead and create our child. So we'll do our fork. If we are 0, that means we're the child, right? Okay, and what does the child do in our situation here? The child listens. Well, the child's probably going to spit out an initial message, right? Maybe saying connected. But then the child is just going to perpetually listen for their connected user to type something, and then they're going to broadcast that message to everyone else except their connected child. Make sense? All right. So we were printing out to the screen connected here, and we can still do that if we want to see at the server level that somebody else had connected. So we'll see that at the server. I'm actually going to just jump down here to the else. Did we not write to the socket in this this example? Oh, it's probably in one of our functions at the top that I didn't copy, so it'd be back in here. Yeah, it's the send stuff. All right, so we'll go ahead and we're going to send a message to that connected client. And this is something that comes with the socket library. All right, so if we are the child, we'll go ahead and print to the screen locally so we see that somebody's been connected. It actually might make sense, just so we don't put this at the child level, if we immediately display connected up here. The server is going to spit out to their screen, new client connected. So we can even just say that. New client connected. Add that client to our list of connected clients. Create a child process to deal with this connected client. If we are the child, we're going to do some stuff. What are we going to do? We're going to send a message to them. The message I wrote up here was called welcome message. So we'll send to this new socket, which is in the local scope for this child, right? We don't have to go and hit shared memory to get the client that was associated with this particular child. He has that local variable. He has that integer. All right, that's called new socket. And we're going to send over that what message? Our welcome message. What length? The length of the welcome message. I don't remember what the 0 was. Was that like auto flush or something like that? All right, so that should show the connected client welcome. And then for right now, I'm going to actually gut the rest of this inside the child, because we're not going to read. We will read some stuff in, but right now, we can actually, let's just make it echo for right now. We'll say printf from client %s buffer. So we will read into our buffer, which was a char array that we built somewhere up here. This dude. In fact, you know what? I'm going to actually bring that down here. The child's getting a copy of it anyway, so we still have to, it's going to recreate new memory anyways. So why don't we just bring that in local to our child. So the child will create a place to capture messages from the end user. We'll then, after we've printed out the welcome message to the child, we'll read in up to 1,024 bytes into our buffer from the new socket, which is in scope for the child. And then we'll just echo that back out to the screen from client, %s, whatever buffer was. All right, we're going to go ahead and get rid of the rest of this stuff. This was us parsing through our thing for our get, our commands and stuff like that. All right, and do I have my main set up to return an int or not return an int? Set up to return an int. All right, so if we're the child, we'll create some place to read in our message. Then we will send that welcome message to him. Then we'll read in whatever the child types one time. Then we will echo that out to not the child screen, but to the server screen. Technically, it'll be to our screen, which is the same monitor that all the children and the server are using. All right, so we'll just see that spit back out. Then we'll go ahead and shut down that socket, even though that's going to sort of break things for us since we're not actually going to ever disconnect. So for us, I actually want to leave that out right now because we're not actually removing the socket from our shared memory of sockets. So we'll just leave it open until we go in and kill our program, just so we're not doing something that we think is doing something else. All right, so from a child perspective right now, all this server does is we get a connection, create a child. Well, we add them to the list of connected clients. We create a child. The child welcomes the new person, waits for exactly one message to come in, and then echoes it to the screen, proving he received that message. We're not broadcasting to anybody. We're not doing any of that stuff yet. Make sense? Okay. So that's what we do if we are the child. If we are the parent, before we were just printing out that we created a child, because that's what the parent does. So maybe we put two little messages here. Printf added connected client to shared mem. And then created a child. Those are the two tasks that the parent does. Okay? We certainly don't have to print it. In fact, the efficient way of doing this would just be to take this entire else out. Okay? Because then what are we going to do following that? We're going to loop back up to this while true. So what does this code do right here? This says server listens forever. That's what that guy does. Okay, server's going to listen forever. Did I spell listens right? There we go. All right, server listens forever. After we have the child, we'll print out, if you're the server, if you're the parent, we'll print out this is what happened. We added the connected child to our shared memory. We created the child process. This dude's going to, well, ultimately this is going to be in a loop where the client will continue to listen to the connected person for longer term chatting instead of a single message like we're dealing with right now. All right. But while that child process goes on and does its thing, the parent's going to loop back up and wait for another child to connect. Rinse, lather, repeat. All right. All right, so let's make sure we got this extra stuff down here because we had some stuff left over from our other program. So we've already done this stuff. We're not doing mem copies in here. We're not doing sleep stuff in here. That was just proving a point. This is when we finally detach. So what we'll do is I'll get rid of that. So in the event that this infinite loop ends, we will want to actually detach from our shared memory. All right. Right now, the only way our infinite loop ends is through the violent decapitation of the Control C on the keyboard that will make our code end, so we don't get out of our I don't think there's a graceful version of killing a process from the shell. I could be wrong, but I don't think there is. I mean, we would probably want to have some sort of shutdown command for the server, where the server will receive some input as well, and we can actually go in and Yeah. Our while having an infinite loop in our while loop is probably not like the best, the best way of handling this. But we're going to do it anyways for the example, right? That part's not what we're learning about here. Okay, so we should now be able to have an infinite number of connected clients where each client is able to send one message to its child process, which then echoes it back to the screen. Not the screen the child's on, but the server screen, because the presumption would be that the child's actually telnetting in from another computer somewhere else in the world over the internet, but we're going to be doing it all from one machine. Okay, so given all that, let's see what we broke. This is in, what folder is this in? 450 something, right? CD, CSC450, haha. All right, GCC server.c, big money, use of undeclared. Oh, did we not bring in the, we just didn't bring in our global variables from this. At the top here, we have our, what are these guys called again? Here, I'll paste it in here, it'll be a little larger. The dollar sign define, what does this create? Remember the word I told you? About 98.25% sure I told you. You guys are called macros. So this creates a macro. It's pretty high performance. So what this happened during pre-processing before compile time, it goes through in any place that you use the word port, it replaces that with the literal 8080. Does that make sense? I mean, so this is not, at runtime, this variable does not get resolved because it's not a variable. This is a search and replace that happens prior to compiling. So this is a performance. This is better performance than putting it in a variable. So something like this would have made sense for our shared memory key, for our max users, all those things. It would make more sense to do that. But again, low on time and I'm lazy. So as good student programmers, you will fix my bad code. I could say that to seniors. That's great. All right. So seemingly it's good. All right. So we'll go ahead and run this dude. Set socket protocol not available. Oh, we didn't run this on the Mac last time. Okay. That's fine. Relax. Let me just copy all this. Let me go into Cloud9. So make sure I give you initial working code to do your impossible homework with. Minutes, come on. I'm going to give it to you as homework regardless. So you either have to fix what's broken or because I'm just that nice. Right, Brennan? Right. Okay, so what was I doing here? Let's just create a new file. Do I not create it? I create it here. New file. We'll call this guy chatserver.c. We'll paste all our stuff in there. We'll save it. GCC chatserver.c/out. All right, this guy is listening. Then we'll go over here and we will telnet, well, localhost port 8080. Oh, that's sad. It's very sad. We got a new client connected. Segmentation fault is right here. I'll point it out, then you guys can fix it. It's right there. I think you have to use memcopy. Nope, that's not going to work either. Recompile. Connect. There's our connected. So you'll have to go back and use memcopy. We couldn't directly add that to our shared memory for our new socket. Was the thing. Okay, so now I should be able to type in LOL. Oh, except that's at the server. I should be able to type in LOL. And then at the server, we have a from client LOL. And if I want to connect from another thing here, telnet localhost 8080 woot back on the server from client woot. Make sense? All right, so you have a mostly working thing. Patch up the shared memory piece and make this work so that it broadcasts the message to all other connected users except themselves. All right, so it should work for the client only needs to, well, no, because that's going to break it. Client needs to keep listening to the thing. So these should be connected permanently, and then the user should be able to type in 50 things, and that should get broadcast to all other connected users that are currently on the system for good. But there's no way to exit, so you don't have to allow them to quit. Sound good? So make version 1 of chat server work. I'll put this code up on Slack and put the assignment up on Blackboard. Remember, the Bible homework is up on Blackboard. It was up earlier this week, but it's not due till midnight on Sunday because I think I got it up on Tuesday or Wednesday. So don't forget to do that.